Hello friends, this is Professor Rahul Bhavne, and in the subject of heat transfer, today we are going to see radiation shield. So let's start today's video. So what is radiation shield? So before we shift over to radiation shield, I just want to revise what we learned in a previous video. So we saw that if there are two surfaces at a different temperature, different emissivity, and then in a case of calculating rate of heat transfer by radiation, so we observe that there is a resistance, radiation resistance, and radiation resistance having two kind of resistance. One is surface resistance. So no doubt such kind of surface resistance for surface 1 as well as surface 2. And second is space resistance. Now surface resistance, suppose I am talking about surface 1. So what is the surface resistance in this case? So surface resistance will be 1 minus emissivity 1 divided by A1 emissivity 1. And what about space resistance? So space resistance depend on the direction of heat flow. So if I am calculating heat flow from 1 to 2, then my space resistance will be 1 to 2. In that case, it become 1 divided by surface area 1, shape factor 1 to 2. If I am talking about heat transfer from 2 to 1, then space resistance will be 1 divided by A2 multiplied by shape factor 2 to 1, like that. And to calculate shape factor, we have a number of properties, but for flat surface, we know that itself it is 0, then use a summation rule and then find out shape factor from this surface to second surface. So we know up to this only. Okay, now we will move on to radiation shield. As its name suggests, it is a shield, and radiation shield, that means the shield which is protecting the radiations. Protecting from radiation, it means it is not allow radiation to transfer through that shield. But it is not possible, that is 100% restricting passing any kind of radiation. It is not possible, for physically not possible, because we have some limitation to manufacture a shield. So after that, obviously there will be a radiation pass through that shield. But what is that radiation shield? So radiation shield is the surface which is introduced in between two surfaces where the heat transfer takes place by radiation. So suppose there are two surfaces and radiation is there in between these two surfaces, and we are inserting a third surface in between two, and that third surface having a property to reduce the radiation, then we can say that third intermediate surface is a radiation shield. Now, as per the technical language, it is said that radiation heat transfer between two surfaces can be reduced greatly by inserting a very thin, highly reflective sheet material. Why thin? Because if it is a thick, so definitely it is going to absorb that radiation heat. So heat will be absorbed within that sheet. Highly reflective. So radiation heat transfer takes place by waves. So we have to put a highly reflective sheet so that whatever be the radiation incident on that shield, it will get reflected back, and it will not allow to pass through that shield. So it will receive by the another surface. So this reflective sheets material in between two surfaces. This low emissivity thin sheet plate are called as a radiation shield. Why again we require a low emissivity? If it having a high emissivity, then definitely it is going to transfer high rate of heat transfer. So our problem will not be solved by that shield if it having a higher emissivity. So we must have low emissivity, so it will emit less heat. We must have high reflective sheets, so it will reflect a maximum amount of radiation reflect back, so it will not allow to pass that radiation to second surface. So because of this, whatever be the total amount of radiation get reduced by inserting such kind of shield. Now what happen actually, as the sheet with a very low emissivity is introduced, so radiation surface resistance become infinite. Remember, inserting any shield will not affect the space resistance directly, because space is the space, okay? So it is not contributing to increase the space resistance in that manner, or space resistance will not play that major role in reducing radiation heat transfer, but surface resistance. Now here we know that what is the surface resistance formula, 1 minus emissivity divided by 1 minus A emissivity. So if it having a minimum emissivity, suppose 1 minus emissivity having a very less value, so definitely numerator will be the higher, and if numerator is higher, so overall resistance will be higher. And we know that if there is a higher resistance, so rate of heat transfer will be minimized. So inserting any radiation shield, we actually using high surface resistance so that our radiation rate will be reduced. Now these radiation shield are not absorbing any radiation heat, also it is not generating any radiation heat. So radiation shield, it is many times asked in practical exam, how it work, how it reduce the radiation. So it is reduce radiation by reflecting maximum amount of radiation by using low emissivity, so that its surface resistance will increase, so radiation rate will be decreased. So it is actually not going to absorb the radiation within, or even though it is not generating the radiation, it is only reflecting back and providing a resistance to transfer heat by radiation. Now where it is used application, so in the field of cryogenic, also in space application, a radiation shield use, and in cryogenic and space application we require maximum resistance. So in that case particularly, whatever be the radiation shield is constructed, it is having about 20 sheets in a 1 centimeter thickness. So imagine 20 sheets, reflective sheets in a 1 centimeter thickness, and all the sheets are separated by evacuated vacuum space. So it is not in direct contact. So all the sheets are separated by vacuum. So such kind of radiation shield is used if there is application of cryogenic or space application. Also we know that mobile, everyone knows that it emits a radiation, okay, and that is a harmful. But it is not the total radiation emitted from the mobile, because mobile casing having a radiation shield. So we received less amount of radiation, even though it is harmful, but we received a less amount of radiation. So mobile casing also having radiation shield, even though mobile towers that having a radiation shields, that are receiving point and all. Now we know that if heat transfer between two surfaces, so what is the formula, what is the space resistance, what is the surface resistance. Now suppose I insert one shield. As I said, radiation shield is having a low emissivity and high reflectivity, correct? Now if I insert one shield here, now how the heat transfer take place now? So suppose, imagine heat transfer from surface 1 to 2, and if I insert a radiation shield, so heat transfer will be first from surface 1 to 3, this shield, and then after from shield to surface 2. But because of insertion of this shield, the total radiation will reduce. Now, what happened? What is the electrical analogy? So, surface 1 having its own surface resistance, 1 minus emissivity divided by A emissivity, surface resistance. Then space between surface 1 and 3 having its space resistance, that is 1 upon area shape factor. Next, this radiation shield having its own surface resistance, this surface that is facing to surface 1. So surface resistance 3 to 1, that is facing to 1 surface resistance. Radiation shield on second face having its surface resistance towards second body. So surface resistance 3 to 2. Then space resistance between radiation shield and surface 2, and again surface 2 having its own surface resistance. So this much resistance will be act if we insert one shield. Now we are talking only about heat transfer from 1 to 2, that's means in between 3. So heat will now transfer from 1 to 3 and 3 to 2 like this, because shield don't have its own radiation. Okay, because as just we saw, it is not absorb any radiation and it is not generate any radiation. Okay, it is used only to reduce, but whatever be the radiation coming from surface 1, it will reduce, but it cannot be eliminate completely. So whatever be the reduced quantity, it will pass through and reach to surface 2. Now electrical analogy, we come to know how it will be now. So heat radiation using electrical analogies. So QR is equal to sigma T1 raised to the power 4, surface temperature of 1, and minus T2 raised to the power 4, because heat is transferring from surface 1 to 2. So T1 raised to the power 4 minus T2 raised to the power 4 divided by total resistance. Now what is the total resistance? So total resistance, we have to add all these resistance because all are in series. So surface 1 plus space 1 to 3 plus surface 3 resistance but towards face 1. Then surface again 3 resistance towards face 2. Here by mistake it comes 4. Sorry. Then space resistance and last surface resistance of 2. Now this is our total resistance. We will put now notation. So what is the surface resistance for 1? So it is 1 minus emissivity 1, area A1, emissivity 1. Now space resistance from 1 to 2, so plus 1 upon area A1, shape factor 1 to this shield. So it is denoted by 3 surface, so 1 to 3 plus surface resistance of shield. So 1 minus emissivity 3, area A3, emissivity 3 plus surface resistance of shield but towards surface 2, it is 1 minus emissivity 3, area A3, emissivity 3 plus space resistance between shield and surface 2. So it will be area A3, shape factor 3 to 2, or even though you can change area A2 because radiation shield don't have its own radiation, own heat generation. So we can use surface area of 2 also. And in this case especially, we have to assume that all shield having same area. Okay, so you can replace this also. So area A2, or you may say area A3. Shape factor 3 to 2 plus 1 minus emissivity 2, this divided by A2, emissivity 2. This is surface resistance of surface 2. Now all these are the resistance. Now all surfaces are parallel. So definitely shield having the same surface area as surface 1 and 2. So we have to use this relation, that is all area are same, and we will denote area as A, common A. So now wherever the A1, A2, A3, so we will replace by A. Now we can take A as a common. So 1 upon area, by mistake here still area is not removed. So area will be like this then. So if I put the total resistance of 1 upon area is a common, so total resistance term will like this. Now if I shift this area to numerator, so it will be our regular form, that is sigma, Stefan Boltzmann constant, then area, then temperature difference, but obviously Kelvin raised to the power 4 divided by this resistance terms. Now we have to separate this. 1 divided by emissivity 1 minus emissivity 1 divided by emissivity 1 likewise. And in addition to this, shape factor. What is the shape factor value? F123. So F11 is having a 0 because it is a flat surface. And if I made a summation rule, so F11 plus F123 must be equal to 1. So F11 is 0, so F123 become 1. So for parallel space, F123 or F322 is 1. Second logic is whatever be the emissions emitted from surface 1, it having the same area, so it is virtually forming a closed loop. So it is assumed that total radiation will be absorbed by surface 3. So we can give the 100%, that is value 1. Otherwise, you can use a property and find out the value of F13 and F32. Now we are replacing that shape factor value 1 and here 1. Now we will separate out this denominator portion, so it become 1 upon emissivity 1 minus emissivity 1 divided by emissivity 1 plus 1 upon 1 plus, here also we are separating 1 upon emissivity 3 minus emissivity 3 divided by emissivity 3 plus second bracket also 1 upon emissivity 3 minus emissivity 3, then plus 1 upon 1, and similarly for surface resistance of 2. Now here emissivity 1 get cancelled, it become 1. Here also 1. So it will be a simple form now. 1 upon emissivity 1, this become minus 1, this become plus 1, so it get cancelled. In bracket 1 upon emissivity 3 minus 1 plus 1 upon emissivity 3 minus 1. Here become plus 1. 1 upon emissivity 2 minus 1, so again plus 1 minus 1 get cancelled. So we have this kind of arrangement. So 1 upon emissivity 1 plus 1 upon emissivity 3 minus 1. Second plus 1 upon emissivity 3 minus 1 plus 1 upon emissivity 2. If we rearrange this, so we have this form. So we will make it in a 2 bracket. So emissivity 1, that is 1 upon emissivity 1 plus 1 upon emissivity 3 minus 1. So this is for these 2 plates. Now for second 2 plates, emissivity 3 plus 1 upon emissivity 2 minus 1. This is for second plate. This is standard notation. We already known that in previous video. Now suppose all the surfaces having same emissivity. This is very important because many times it is asked in your practical exams, oral exam. Suppose all surfaces having same amount, same quantity of emissivity. In that case, we have to replace all this emissivity by simply emissivity symbol. So it will become like this. So heat transfer from 1, 3, 2. So it will be 1 upon emissivity plus 1 upon emissivity minus 1. Plus 1 upon emissivity plus 1 upon emissivity minus 1. So this is our final form. So it can be written as twice of this bracket. And it is nothing but half of emissivity, half of sigma area temperature raised to the power 4 difference and divided by this bracket. And what is this whole quantity? So this whole quantity belongs to the rate of heat transfer from 1 to 2 if there is no radiation shield. So if there is no radiation shield, but surface 1 and surface 2 having same emissivity, then in that case, if you are going to calculate a rate of heat transfer from surface 1 to 2, then our answer will be this one, sigma area in bracket T1 raised to the power 4 minus T2 raised to the power 4 divided by 1 upon emissivity plus 1 upon emissivity of second surface minus 1. So this will be the total equation for rate of heat transfer without shield. And if we insert a shield and having the same emissivity, so our formula become half. So our equation is rate of heat transfer if there is a one radiation shield, 1, 3, 2 will be half a rate of heat transfer without radiation shield. But when this is possible? Only when all the surfaces having same emissivity. Remember this, when all surfaces having same emissivity, then whatever be the rate of heat transfer, if I am inserting one shield, it will be half of without shield heat transfer. So what is the generalized equation? Suppose I insert an n number of radiation shield. So practical examiner always asks this question. Suppose there are 10 number of radiation shield, then what is the rate of heat transfer between two surfaces? So 10 radiation shields are inserted in between two surfaces, then what is the rate of heat transfer? If one shield is added in between two surfaces, so rate of heat transfer become half here, half. So generalized equation, if we insert n shields in between two surfaces, so rate of heat transfer will be 1 upon n plus 1 of without shield heat transfer. So if I take it out, so it will become 1 divided by n plus 1, and whatever be the remaining term, it is a rate of heat transfer between two surfaces without shield. So if there is n number of sheets, so what is the rate of heat transfer? 1 upon n plus 1 times of without shield rate of heat transfer. So suppose my question as an examiner, suppose without any shield there is a rate of heat transfer 100. So what is the rate of heat transfer if I insert two radiation shield in between two? So n is 2. So n plus 1 become 3. So 1 upon 3 times of 100 will be the rate of heat transfer. Now we will see one numerical. Two large parallel planes A and D. So two surfaces are there, and it is said it is a large and parallel, are maintained at a temperature of 1500 Kelvin and 600 Kelvin respectively. Emissivity of A 0.9, emissivity of D is 0.4. Two radiation shields B with emissivity 0.5 and C with emissivity 0.2 are inserted in between them such that A, B, C, D are placed one after the other. Now, one point you must be noted that all having different emissivity, so we can't use that generalized form. Okay, that is only applicable when all having a same emissivity. And it is asked to calculate heat transfer rate without radiation shield. Second, heat transfer rate with radiation shield. So we have two radiation shield in that case, and temperature attained by plane B and C. So obviously radiation shield will attain some temperature. So we have to calculate what is the temperature of that inserted radiation shield. What is given? So emissivity A is given, its temperature is given. Emissivity D, second surface, is given, its temperature given. Emissivity of radiation shield B and C is given. And as it is said, large parallel plane. So obviously all having the same area. So area of A, area of B, area of C and area of D will be equal and we will note it as a A. So this is our given data. Now we will solve one by one. So first is heat transfer without radiation shield. So suppose there is a plate A having area A, temperature A and emissivity A. And this is plate D, area D, temperature D and emissivity D. And there is no any radiation shield inserted. So in this case, what will be the electrical analogy? So surface resistance of A, space resistance from A to D and surface resistance of D. How we decided heat transfer will from A to D? Because A having higher temperature 1500 and D having 600. So we are only calculating A to D. Definitely whatever be the body having temperature more than absolute zero, it is also radiating heat. But here we are considering as per temperature difference only A to D. Now we know what is our equation. So heat transfer rate when there is no radiation shield. So sigma area temperature difference raised to the power 1 upon emissivity plus 1 upon emissivity minus 1. So here two plates. So emissivity A, emissivity D minus 1. We will put the value, but we don't know the area. And it is said area are large. So we assume that area for both the sheets are same. So area. But area value we don't know, so we are going to calculate per unit area. So Q by A. Sigma temperature raised to the power 4, that is the difference, and then emissivity. Put the values, we know sigma standard value 5.67 multiplied by 10 to the power minus 8. Temperature already given in Kelvin, so no need to convert into Kelvin. And then emissivity 1 upon 0.9 plus 1 upon 0.4 minus 1. So on calculating, we come to know that if there is no radiation shield, rate of heat transfer is 107163 watt per meter square. Now suppose two radiation shields are inserted, B and C. So what will be our electrical analogy then? So this is plate A and this is plate D. And we are inserting two plates now, plate B and plate C. Now heat is definitely transferring from plate A to D, but through B and C. So heat transfer rate A, B, C, D. Now accordingly we have space resistance between A and B, surface resistance of B, surface resistance of B towards plate C, space resistance. So all these we have to calculate. So our equation become rate of heat transfer in second case, sigma area, because area remain common, temperature raised to the power 4. Now what is the resistance? So we know that on simplifying, we always get 1 upon emissivity of first plate plus 1 upon emissivity of second plate minus 1. Here first plate is A, second plate is B. So it will be for 1 upon emissivity A plus 1 upon emissivity B minus 1. Plus now for these two plates B and C. So emissivity B plus 1 upon emissivity C minus 1. Now third part from plate C to D. So again bracket 1 upon emissivity C plus 1 upon emissivity D minus 1. So not required to go again to simplify this and finding all individual resistance and come back to this final form. So whenever it is asked, so hereafter we will use this standard form. Now here also we don't know the area, so we will shift area and we calculate Q by A for second case. Now putting the values, because all the emissivity values it is given. Temperature only we require for A and D. So after calculating, we come to know that this time when radiation shields are inserted, so your heat transfer rate is 19144.11 watt per meter square. So it must be reduced because radiation shield are used only for that purpose. Now the final form part, that is the temperature of radiation shield. So we have two radiation shields. So temperature of B and temperature of C. So this is our electrical analogy, if I am interested to find out the temperature of B, so I will use only plate A to B, this portion. So considering only plate A to B, so heat transfer rate Q by A. So Q by A remains same throughout the system, and Q by A we already calculated, but for plate A to B, so our equation becomes sigma Ta raised to the power 4 minus Tb raised to the power 4, and resistance will be, denominator will be 1 upon emissivity A plus 1 upon emissivity B minus 1. Put the value Q by A from previous answer, remaining all values are given, only the Tb is unknown. So rearrange it, simplify, then it becomes Tb raised to the power 4. So we have to take a fourth root of this. So it will be like this, fourth root, and hence we come to know that Tb is 1444 Kelvin. Now in the same manner, if I am interested to calculate the temperature of C, so I have now two options. Either I will choose plate B to C, or I will choose plate C to D, any two plates. So here I am using plate C to D, this second pair. So Q by A, sigma Tc raised to the power 4 minus Td raised to the power 4 divided by 1 upon emissivity C plus 1 upon emissivity T minus 1. So it will be become like this. Simplify this, rearrange. Now we have to take a fourth root. So fourth root, it will give the temperature of plate C. It is 1235 Kelvin. And remember always how to tally your answer is correct or not. So temperature must be reducing. So from plate A to D, it must be reduced. So it is 1500, it is something 1444, it comes 1235, and it is 600. So reducing. So thank you.